In Chapter 7, we're going to start talking about probability, density functions, cumulative distribution functions, and then an application of mean and median. In order to talk about all these probability topics, we need to understand integrals, hence why we had to talk about integration by substitution and integration by parts before we talk about this material. To introduce the density function, we're going to take a look at this distribution of ages of US citizens in 2012. Note that this example is taken from the text, and we're not going to consider people greater than 100 for the ease of this problem, and also that just is going to represent a very tiny percentage of the actual population. So what this table is going to say is that for each age group, we have 0 to 20, 20 to 40, 40 to 60, 60 to 80, and 80 to 100. We have a percentage of the total population. So 27% of people in the United States in 2012 are between the ages of 0 and 20, whereas 15% of the people are in between the ages of 60 and 80. So we're going to use that information to build a histogram, which is seen below of this data. One thing that we're going to do beforehand, and we'll talk about why we're doing this in the next couple pages, is that we're not going to use the values of 0.27, 0.28, 0.15, and 0.03. We're not going to use these values, but instead we're going to standardize these values by dividing by the number of years in each group. So since these groups have 20 years in each group, we're going to divide each of these populations by 20. The reason we're doing this is because we are going to look at histograms on the following page that have to deal with age groups that are smaller, and we can compare these if we've divided by that number. So I've done the calculation here, the fraction of population per year of age. Take the number, divide by how big that age group is, and we get these values out. These values are not going to be particularly interesting to us by themselves, except to kind of draw this picture and to understand what's going on here. So, to draw this picture, if we think about the ages 0 to 20, we're talking about this age range as the x-axis is going to represent years. And we draw a bar here up into the line of 0.0135, which we get from that first item on the table. And this is going to give us a fraction of the population. If we take the area of this bar, it is going to be the 0.0135 times 20 years will give us our 0.27. So this fraction of the total population is corresponding to the area of these bars. We'll do it again. This bar right here, from 60 to 80, corresponds to the y value of 0.0075, which means that this area is 0.0075 times 20, which is going to give us our 15%, or 0.15. So the fraction of the total population is the area of the corresponding bar in this histogram. And this is why we want to divide by that 20, so that one, we can compare different histograms, but two, that the area is the special value, and we know that area is related to integrals, and that is going to be something we're going to investigate in the next couple pages. So given this histogram, it gives us the distribution of ages. We can ask some questions about the percentage of people with certain ages. So, for instance, what percentage of people in the US are greater than 60 years old? What that is going to represent in this picture is we're going to look at everything greater than 60. So we're going to look at this bar and this bar, and we're going to find the area of those. And the area of those are going to be 0.15, and this area is going to be 0.03. We get those values from the table right there. Or we could just do the what we did before, 0.0015 times 20 to get the 0.03, so on and so forth. So what percentage of people in the US are greater than 60 years old? It's going to be 0.15 plus 0.03, 0.18, so that means 18%. All right, so what we're going to do now is instead of looking at age groups of 20 years, we're going to shorten the age group and we're going to look at 10 years instead. So here is the same data, but now we're going to break it up into 0 to 10, 10 to 20, and into the different decades. So same thing applies. Note that the fraction of population divided by the year of age is now we are dividing by 10 because that is the length of the age. That's how many ages we're considering in there. This is our standardization of these histograms so that we can compare. And we get the same bar chart out. For each bar, we look at the corresponding Y value. That Y value in this case would be 0.013. And the area of this bar is the 0.013 times, in this case, 10 would give us the 0.13, 13%. And again, we can ask questions such as, what percentage of people in the US are between 10 and 30 years old? So here we're going to be looking at everything from 10 to 30. We're going to be looking at the area of these two bars, which will give us 0.14, 0.14 for both of those, 0.28, so 28%. So let's continue this process. Let's even narrow the age range a little bit more. Let's do 5 years of each age range. This time we're going to have 20 bars here. I'm not going to have the whole table. And in fact, this is not going to be quite accurate. We'll be sort of the same here. Note that if we look at one of these bars real quick, so if we look at the original bar from 50 to 60, the two bars that are now breaking up in between them, the total area will equal the area from 50 to 60. One is bigger, one is smaller. We know that this area is going to cancel out with this area, and they're going to be equal to each other. So we look at this histogram and we think about if we can even narrow the age range even further, and we can just continue to narrow it on and on and on. We could have a difference of 1 year in each age group. We'd have 100 bars. We could even do half years and go further and further. In fact, we could do that indefinitely until we have an infinite amount of bars. Instead of doing all of that process, what we're going to do is something called smoothing out the curve. So instead of decreasing the age range further and further and further, we're just going to hypothesize what this curve is going to look like. So I'm going to draw a possibility of this curve. It's going to match up about with the tops of those bars that we found in the 10-year age gap. So maybe something like this. Okay, that's a little hiccup there. Something like that. So that is the smoothed out curve. This is what we are going to call our density function. And we're going to call this P of X. We'll investigate what that means on the next slide. So going back to what we talked about in the previous problems, we can answer questions like, what percentage of people in the US are less than 23 years old? We look at the x value of 23, and using this curve, we are looking for the area under that smoothed out curve. In order to find an exact value of this 23, we'd have to have all the data of people within 1 year gap, but now we can just do it with this density function p of x. So we know stuff about the area under a curve. We know that this is going to be the integral of p of x dx, and bounds are going to be 0 to 23. That is the area under that curve to the x-axis, again from 0 to 23. So now let's introduce the density function formally. So again, the smoothed out curve is called the density function. We're going to call that p of x. P is going to be standing for probability. That's why we're using this letter here. So the function p of x is a density function if the fraction of the population for which x is between a and b is equal to the area under the curve of p of x from a to b. Again, that is the integral from a to b, p of x dx. We saw on the previous page, we asked what is the probability, or what is the percentage of people that are less than 23, so from 0 to 23, and we found that that was equal to the integral because we had a density function. That's what we're saying there. There are some things that we know from density functions. So if I take the area from negative infinity to infinity, so this is the, call this maybe the total area, this will give us the fraction of the total population, which will be 100%, or 1.01. So that's what that's saying. From negative infinity to infinity, we're saying everything included, that's going to be 1. For our population example, we're saying that maybe the integral from 0 to 100 of p of x dx would be equal to 1. It doesn't necessarily have to start at negative infinity to infinity for all applications. We also have that p of x is always going to be greater than or equal to 0 for all x, as we're going to think of p as a probability, and we're never going to have the probability of something or a percentage of something be less than 0. So p of x itself represents, we should say, so p of x the percentage of people with, in this case, age, we're going to say about equal to x. So, for example, p of 20 would be the percentage of people that are 20 years old or about 20 years old. So that means that p can never be less than 0 because the percentage of people that are a certain age cannot be less than 0. It could be 0, but can't be negative. All right, and we're using this example of population, but note that this does not have to just stay with population. We're going to use p of x for a wide variety of applications. And we're also just going to be dealing with some simple density functions most of the time, or ones that have a formula that are going to be easy to anti-differentiate. We're doing integrals, so we are going to anti-differentiate in this problem. And in section 7.2, we're going to talk about what the antiderivative of the density function is. So last thing before we talk about practice in the next video is something called the bell curve. This is a thing that's well known, even outside math circles. We're going to talk about what this means in terms of a density function. And we'll look at a common example, maybe the height of adult Americans. We know that the mean height for an adult American is about 5'8", and we know that most people are not going to be less than 4 feet or greater than 7 foot 4 feet. So we can draw this density function here. That's going to look like this. And this is what we call a bell curve. There we go. That is a bell curve. The middle here is the mean, which we'll discuss in 7.3, some examples of mean and median. But we also know that the area under the bell curve will give us the fraction of the population. So if we're thinking about how many people are above 7 foot 4, the area here will give us the percentage of people above 7 foot 4 inches, which is not going to be a lot of people. Whereas if we found the area of people who are in between or around 5 foot 8, that's going to be the majority of people. Right? This is a common application of the density function. This line is the density function. This is sometimes called a normal distribution. This density function has a formula that's going to be something like e to the negative x squared, but we're not going to discuss all of those details in this course. In the next video, we're going to look at some application problems and some practice with these ideas.